was problem 2, part C. The prompt for this problem is a free neutron that is on the outside of a nucleus is unstable and decays into a proton and an electron and an antineutrino. The mass of the neutron is 1.67 times 10 to the negative 27 kilograms. The mass of the proton is 1.67 times 10 to the negative 27 kilograms. The mass of the electron is 9 times 10 to the negative 31 kilograms. The mass of the antineutrino is much smaller than the electron mass, and it can be assumed to be 0 here. In part A, we solved for the total kinetic energy of all 3 products once they were very far apart, so like the final kinetic energy, the final state being that all of the products are really far apart from each other. In part B, we solved for the potential energy when right after the products had decayed, because right after the products decay, there was a proton and a neutron. We know those repel each other, so we know there's going to be a lot of potential energy right there. So that's what we saw for in part A and B, and those will both help us with part C. Part C's question is, what is the total kinetic energy immediately after decay? So I jumped the gun a little bit in this problem and said that immediately after decay, the particles had only potential energy and weren't moving, and I said that it was 0. But this is not the case. If you say immediately after decay, like a few seconds is immediately after decay, and you solve for it that way. So the first way we're going to break this down is we are going to look at we're going to pick an initial state and a final state, and we're going to use the energy principle to solve for kinetic energy, to solve for the initial kinetic energy. So if we say the initial state is what we're looking for, which is immediately after decay. And if we say the final state is when the particles are really, really far apart from each other. So like in part A, we found the kinetic energy for that. Far apart. Okay, so what we're going to look at here is between the initial state and the final state, we know that there is no change in overall energy because energy can't be created or destroyed. So the change of energy must be 0. And there are 3 different types of energies that can change, but added together, they must be equal to 0, the changes in them. And the 3 that are changing in this situation are the kinetic energy, the potential energy, and the rest energy. And the rest energy is changing in this case because the masses are changing, but usually the rest energy doesn't change because it's just mc squared. Okay, so in our case, in the initial state, we are looking for that kinetic energy. So kinetic energy initial, not final, is what we're looking for. Okay, the potential energy initial we solved for in part B. So U initial is from part B. And the rest energy we can just solve for using the equation mc squared. Okay, then the final state we solved for the final kinetic energy in part A. We know that when they're really, really far apart, the proton and electron aren't really going to be affecting each other anymore, so there's not going to be any potential energy when they're really far apart. So potential energy is 0, and again, the rest energy we can solve for using mc squared. So that is pretty straightforward. So now we're going to set up an equation using all of these, knowing that the change of energy equals 0, and the change of energy equals the change of kinetic energy plus the change of potential energy plus the change of rest energy. We can go ahead and say, now I'm going to use black so you can really read this. We can go ahead and say that 0 equals the change in kinetic energy, so K final minus K initial. K final, which is what we found in part B, minus, not equals, minus K initial, which is what we're solving for, plus the final potential energy, which is 0, minus the initial potential energy, so minus U initial, which is what we saw for in part B, plus the E rest final minus the E rest initial. And in our case, since the initial state is right after decay and the final state is when they're really far apart, in the initial and final state, we know that we have the same particles. So we know we have the same mass in both situations, and obviously c is the speed of light, so that doesn't change. So our rest energy is not going to change in this case. We could solve for both of the rest energies, but they would just cancel out in this equation because they're going to be the same thing. It's the mass of the proton, the mass of the electron, and the mass of the antineutron times c squared in both of these cases. So they just cancel out. Okay, so now we're solving for this piece right here. And we've solved for these two pieces earlier. So we can rearrange this equation to say that our K initial equals our K final minus our U initial. And we can plug in our numbers that we got from part A and part B, and I'll go ahead and tell you what those numbers were. In part A, I got 1.26 times 10 to the negative 13 joules. And in part B, so we're going to subtract it, I got negative 2.304 times 10 to the negative 13 joules again. So when we add these together, we get our final kinetic energy, our initial kinetic energy, which is what we were solving for, and we get 3.564 times 10 to the negative 13 joules. And that is our answer. It was a pretty straightforward problem, pretty easy. We just have to remember that you actually have to solve these quantities. You can't just say it's 0. Thank you so much for watching, and I hope I helped.